Now let's talk about Carnot's theorem. Before we talk in detail about this, let's define it first of all. So Carnot theorem states that of all heat engines between a given constant temperature source and a given constant temperature sink, none has a higher efficiency than a reversible engine. So for example, I have this as my temperature source T1, and this is the temperature sink T2, and we know that T1 is higher than T2, and we have all these engines working between these temperature limits. Okay, so let us have three engines. So this is what we get: the heat input and rejection and the work output. Now this is engine 1, 2 and 3. Now out of these three engines, engine number 3 is a reversible heat engine. So this is reversible. Okay, so as per the Carnot theorem, the efficiency of engine 3 would be highest. It will be higher than efficiency of 1, and it will be higher than the efficiency of 2. You cannot comment on the efficiency of engine 1 and engine 2 because there is no comparison given to us between them. But of all the three, the third one will have the highest efficiency because it is a reversible heat engine, and a reversible heat engine is one which is the Carnot heat engine. So in a nutshell, you can say that as per Carnot's theorem, Carnot's engine has the highest possible efficiency. And now let's have a look at this figure given to us. So it has two heat engines, engine EA and engine EB. They are working between the given source at temperature T1 and at temperature T2, and again this assumption is valid, which is T1 is more than T2. Now let us say EA is any heat engine. So this is any normal heat engine. Alright, and EB is a reversible heat engine. Okay, so this is a reversible heat engine. Okay, now we have to prove it, or we have to prove this, that the efficiency of engine B is more than the efficiency of engine A. So I can write down to prove we have efficiency of engine B is higher than efficiency of engine A. Now to prove this, let us assume that this is not true, and with this not being true, let us say let efficiency of A is greater than efficiency of B. Let us say this is true and this is not true. Alright, so we can say that the rates, or we can assume that the rates of working of the heat engines, that is EA and EB, are such that Q1A, that is the heat which is being absorbed by engine EA, is equal to, this is 1B, this is not 1A, this is 1B, is equal to 1B. That is the heat absorbed by engine EB, and this is equal to Q1. So the amount of heat that is being absorbed by both the engines is same, and this is how we can say that both the engines are working. Okay, now we have assumed that this is a true statement, that is eta A is more than eta B. Now eta is equal to work done upon the heat supplied. So this is the value of the efficiency. So by applying this concept, I can say that WA, that is the work output of engine A, upon Q1A is greater than WB upon Q1B. Now we have just assumed that Q1A is equal to Q1B. Okay, so they can be cancelled off. So this gives us a relation which is WA is higher than WB. Okay, now let us reverse engine B, because we said that the engine EB is a reversible heat engine. So let us now reverse it. Now when you reverse engine B, you come to this figure. So this is engine A, which is not reversed, but the engine B is now reversed. Now because it is a reversible heat engine, the magnitudes of heat transfer and the work transfer, they remain the same, but their directions will be reversed. So this is how you can look at the diagram when you reverse engine B. Now we have this, that is WA is more than WB. Now this means that some part of WA, that is the work which is coming out of engine A, okay, some part of WA, and that some part of WA is equal to WB. It may be fed to drive the reversed heat engine EB. Okay, now what is happening? That as WA is higher than WB, I can write that WA is a sum of WB plus some quantity X. Okay, so WB is a part of WA. So what I am saying is that because EB is a reversible heat engine, and since this is true, some part of WA, and that some part of WA is equal to WB, which is fed to drive EB. Alright, or you can say the reversed heat engine EB. Okay, now since Q1A is equal to Q1B is equal to Q1. So if this is what we assumed when we started analyzing this diagram. Okay, so the heat which is discharged by the reversed heat engine, that is Q1B, okay, it can be supplied to heat engine EA. So when this starts to happen, because this heat coming out is same as this heat which is going into EA, so when this starts to happen, you can eliminate the temperature source T1. So this is how your diagram will look like now. So now we have eliminated the temperature source T1, and the net result of this is that the heat engine EA and the reversed heat engine EB, they together constitute a heat engine which is operating in a cycle. So this is a cycle in which this is rotating. Okay, the combination of the two, right? And it produces a net work WA minus WB, because I said that a part of WA is fed to run the reversed engine, and the whatever is left is the net work output of this heat engine. Now this is the net work output, while this engine is exchanging heat only with a single reservoir at T2. Now when this starts to happen, it violates the Kelvin-Planck statement. Okay, so this is the violation that happens if we assume that eta A is greater than eta B. So this means this assumption is wrong. We cannot have eta A higher than eta B. So this means the correct proposition would be that eta B is greater than or equal to eta A. You cannot have eta A greater than eta B. This means eta B, that is the efficiency of a reversible heat engine, is higher than the efficiency of any normal heat engine. Okay, so this is what proves the Carnot theorem. Okay, now after having understood the Carnot theorem and having proved it as well, right, now after this let's understand a concept which is also very important, that is absolute thermodynamic temperature scale. And this is also a topic which makes use of the concept of heat engine and the second law.